In this lecture, we are going to discuss activation functions that can be used as building blocks / layers in neural networks. Some general comments about activation functions. Typically, activation functions have one input and one output. That is true for popular activation functions such as Sigmoid, 10H, RRelu, Leaky ReLU, and there's one notable exception, Maxout. And also typically activation functions do not have a learnable parameter that the network can train on. So these functions have no trainable parameter. Again, this is true for almost all activation functions, and there are exceptions such as the parametric ReLU function. And in the following, it is therefore important to distinguish between hard-coded constants that are just set but that are not trained, and a trainable parameter. While all the activation functions will be plotted and shown as functions with one input and one output in the following, then the activation functions, when they're implemented, they will operate component-wise on a tensor. So if we, as input, receive a tensor that has a width and a height and the depth, then the activation function will simply operate on each element, and so the tensor that you get as output will have the same size as the tensor that you get as input. Let's start with the sigmoid function. The sigmoid function is defined by 1 divided by 1 plus e to the power of minus x. If we look at the plot, then the input is plotted on the x-axis and the output is plotted on the y, the up-axis. We can see that the range of the sigmoid function, the output range, goes from 0 to 1. However, 0 and 1 is not really achieved. What happens is that if we go along this negative direction and the numbers become smaller and smaller, then this sigmoid function approaches 0. And if the numbers get larger and larger, the sigmoid function approaches 1. If we are at about 10 or minus 10, then the sigmoid function is already really close to 1 or 0. This sigmoid function has historical importance. It was used in the beginning of neural networks, and it's somewhat loosely related maybe to the firing rate of a neuron, where you assume that 0 means the neuron is not firing at all, and 1 is the assumed maximum firing frequency. Also, the sigmoid function gives a nice interpretation as probability, where you have the values between 0 and 1, so you can interpret this as probability. Now, we've looked at one activation function, and we want to discuss several properties of activation functions that people look at. There's a general warning that while these properties are discussed by several authors and they're discussed in reviews, and that these properties are presented often as a conjecture of why one activation function performs better than another, the final results are still very inconclusive. As we'll again discuss in the end, the question of what activation function to use and how an activation function performs is very context dependent. So let's look at several of these properties. How large is the derivative gradient of the activation function? So, for example, the sigmoid function can saturate and kill gradients. The gradient is very small, far from zero, so at plus 10 or minus 10, it is almost zero. Here's a visualization of the sigmoid function together with its gradient, shown as a dashed red line. And what we see here is that the gradient, the derivative, is mainly significant around zero, but if we go far out to the positive or negative direction, then the gradient is almost zero. The algorithms that we use to train neural networks use the gradient to update the weights of the network. So if the gradient is close to zero, then the updates to the weights in previous layers will, or the same layer, will stop. And then the gradient is not exactly zero, so it will not completely stop, but it can be very, very, very slow. So while the exact dynamics of the training is a bit too difficult to discuss and summarize just for this problem, the idea is that in general, very small gradients that are close to zero cause a problem for learning and the training algorithms. Also, if, for example, during the initialization, you get some random values that let the output be, or where you have an input that is very large or very small, then the gradients will be small, and it might be difficult to get away from the initialization and the initial values. So it could take, again, a very long time. The next question to ask is, here, is the output zero-centered? Without giving an exact definition of what zero-centered means, we can clearly see that the sigmoid function is not zero-centered. Importantly, the sigmoid function only outputs positive values. For a zero-centered function, we would somehow expect that in some part the outputs are positive, and then in another part the outputs are negative, maybe even forming, that the curve forms a similar shape in the positive region and the negative region. Going back to this list, there is one particular observation that we can make. Let's say, for example, we have a layer that has a computation of the following form. For example, a linear layer. We take the sum over the input values times weights, which are network parameters, and maybe there's also some offset that is a network parameter. If we compute the derivative with respect to W, these are the network parameters, we can observe that if all the xi's are positive, then all the, because there are other things that go into the derivative as well, then all the derivatives of the wi's will have the same sign. So they can all be positive or they can all be negative, as we will see later in a lecture on backpropagation. Now, it's not exactly clear how that influences the training dynamics, but in some sense it seems a bit weird if the update to all the parameters is kind of coupled in some strange way. And if you think about this phenomenon, then if you look at not only one sample but multiple samples, then this effect will be decreasing, because summing up the derivatives gradients of multiple samples, then we will see that some of the weights by summing the gradients can go positive and some go negative. But nevertheless, this is an interesting observation about the training dynamics. Next question to ask is the function smooth? Again, looking at the sigmoid function, probably you have to look at the equation. You can know the function is smooth, and you not only ask, is the function smooth, but often you also ask smoothness of derivatives. How expensive is the function to compute? The sigmoid function is a fairly expensive function because of the e to the power of. The exponential function is expensive in comparison to plus or multiplication. This is a bigger concern on mobile devices and CPUs than on GPUs, because often in GPUs the data transfer might take a long time, and then transferring the data is a bigger bottleneck than the actual computation. Now, these things, of course, change over time and change with the architecture, but in general, it has been true that sigmoid is significantly more expensive than cheaper functions, such as the RRelu function. In particular, one of the early papers, AlexNet, that really started all this excitement about deep learning, it showed that by changing the activation function, it could achieve a 6 times speed up, which is very significant. So another thing that is related to more recent activation functions is the function monotone and is the derivative monotone. Looking at this, the sigmoid is a monotone function. It has a derivative of constant sign. It just gets bigger and bigger and bigger and bigger, and it never goes bigger and then smaller. Now, that seems to be a totally obvious choice, that the activation function should be monotone, but surprisingly, recently people had big success using activation functions that are not monotone. Does the function approximate the identity near zero? This might be maybe a better way to phrase this problem of is the output zero-centered? What people argue sometimes as a good quality of an activation function is that around zero, the function approximates the identity. So around zero, you would actually like the function, the identity function would go around here. Okay, so having these quality criteria or these attributes in mind, we can now look at multiple other functions that are used as activation functions. The 10H function given by this equation looks very similar in shape to the sigmoid function, but it seems a lot more balanced or symmetrical in some sense. So you can see that the output is in the interval of -1 to 1, and the saturation is like the saturation of the sigmoid function. So we also have the problem of gradients being close to zero for very large or very small values. But here we can see that the output is zero-centered, and the function looks similar, or at least compared to the sigmoid function, it's more similar to the identity around the origin. In fact, the 10H is simply a scaled and shifted sigmoid function. The relationship is as follows: 10H of x equals 2 times sigmoid of 2x minus 1. This now is the default choice for activation functions, and this is the RRelu function, defined by max of 0 and x. That means that for positive inputs, the RRelu function gives the input back exactly as output, and for negative values, it clamps to 0. So the output for any negative value is 0. For the input 0, the output is 0. And for any positive value, the output is the same as the input. So that means the output is in the interval 0 plus infinity. And this is, again, going back to this paper AlexNet, where Krzyzewski et al. Said that using the ReLU compared to these traditional activation functions 10H sigmoid gives us factor 6 speed up. It's very simple to implement, and there's one thing to note that is a potential disadvantage, is that the ReLU units can die. So let's just think that we have a whole data set, and the output of the ReLU unit is always 0. So whatever sample we feed in, the output is always 0. Then this ReLU unit is useless for our neural network. And also, we cannot really change it to make it useful, because when the output is always 0, there's again no gradient signal flowing backwards. There's no gradient signal that helps us to update the parameters of the network. There's some conjecture that maybe this even happens more for larger learning rates. And one thing to note here is that somewhat this is surprising. It seems that the ReLU activation functions would lead to this catastrophic failure, which are dead ReLUs. However, in practice, it seems it doesn't actually matter that much. In the same way, this gradient signal in the negative part here doesn't exist. Again, it's 0, so there is no gradient signal that can be used when the ReLU has a negative input and has a 0 output. That also seems very undesirable, but for some reason in practice, it doesn't matter that much. So still, people thought having the output be 0 for all negative values, that just can't be good. Can't we at least have some gradient? Can't we at least have some derivative here to allow learning to happen? Looking at the equation of the Leaky ReLU, we can see that for positive values, the output is the same as the input. So for positive values, the Leaky ReLU is identical to the ReLU. However, for negative values, the output is not 0, but it's a very small constant times the input. Let's look at the visualization of this function. So it looks almost like the ReLU, but here, this part here is not exactly 0. It's still a linear decrease that gets smaller and smaller, but you can see the decrease is very small. So it's just barely below 0 here. In fact, looking at the default parameter for this slope, it's 0.01. So it's just a very small slope. But nevertheless, there will be some gradient also for negative inputs. Now the output is in the interval -infinity plus infinity now, and this parameter where the default is 0.01, you can set it to whatever you want. It's a hard-coded, not learnable parameter. The idea is that these leaky ReLUs cannot die because there is a gradient for positive and negative inputs. And this is, again, the idea is super intuitive. It seems to be a clear improvement over the ReLU. However, in practice, this improvement is inconsistent. So this is the idea of the Maxout. And it's somewhat an activation function that doesn't really fit the standard model of activation function with one input and one output. So the idea here is to say that the neuron outputs multiple possible values. So instead of one neuron outputting only one value, now one neuron outputs multiple possible values. And then this Maxout activation function would take the maximum over these multiple possible values. Now, thinking of the neural network processing tensors, one could somehow think of this as you take multiple channels and then you compute the pixel-wise maximum. And then computing the maximum across multiple channels is not really a dominant ingredient to modern neural networks. It is more common to use other ideas such as one-by-one convolutions, which maybe allows the network to use more of the information. Maybe the problem here is that too much information gets thrown away because you're computing k channels, so to say, but then you're only using the maximum. So maybe there's a lot of computation, and after that only one value is kept. So this is a visualization where you see from left to right, you have multiple different functions that a neuron computes. And so, for example, here you have, let's say one function would be this function here. So these are linear functions. So one possible function would be this one here, another one would be this function here. Then we have one function here, one function here, and then one function here. And the red line shows the maximum of all these blue functions. That would be the output of the Maxout. Going back to the idea of the Leaky ReLU, one can say, why not make this slope a learnable parameter? So this is the equation that is identical to the Leaky ReLU, with the only difference that this value here is now a learnable parameter in the network. Some other comments. The initial value in PyTorch is 0.25 by default, and also a hint on regularization. This would be, for example, a parameter where you would like to use a different type of regularizer. For example, PyTorch recommends to have no regularizer on the parameter A. There's a paper that describes this idea, and you can look at this paper by clicking on the link in the course notes. Here we see the activation function ReLU 6 that consists of min, max, 0x, and 6. So it's identical to the ReLU function. However, it is clamped to 6 for values larger than 6. So why would there be such a weird activation function that is available in PyTorch? And the idea here is that this activation function might be useful for mobile computing and fixed point arithmetic. We're not going into details about this, but this is just a general reminder hint that if one designs neural networks for weaker computing architectures, then the network design often changes, and particular design choices have to be made that are specifically beneficial for mobile computing, for example. Here you can see the exponential linear unit. Looking at the graph of the function, we can see that for the positive inputs, the function behaves like the ReLU, but for the negative inputs, it's slightly different. So we see that around the 0 inputs, the function can still attain negative values, and then it smoothly tapers off. So one thing here is that for all values there is some gradient. Of course, the gradient becomes very small for values that are very, very small, very negative. But we can see that we have now positive and negative outputs, and that this function is maybe similar again to the identity around the 0 value. The parameter alpha has a default value of 1 in PyTorch, and again, alpha is not learnable. The equation is somewhat interesting because it gives you a scheme to combine two different functions. In this particular equation, we combine the function x and the function alpha times e to the power of x minus 1. So this max 0x takes this function x, and it only takes the positive outputs of this function. So it only takes the function whenever the outputs are positive. And this, conversely, it takes this function, but it only uses it when the outputs are negative. And then you cannot use arbitrary functions. They need to, in some sense, fit nicely together to use this scheme. But this is a general scheme to write, to have a way to combine two functions together into one equation. So here's another idea, the random ReLU. This is similar to the Leaky ReLU, where the equation is the same, but now this parameter a, that is this negative slope for the negative part, is randomly sampled in an interval that is from lower to upper. So these are hard-coded in some sense, so they're not learnable, but they are randomly sampled. There's a paper about this, and the authors claim some success with this random ReLU. Now, this is mainly to show it as a novelty idea. This is not something that has been picked up by other authors. However, it shows a bit this really wide range of activation functions and this wide range of ideas that people have tried out. This is the CLU activation function, which is very similar to the ELU function, except we have a scale here, and there's a recommendation for this parameter alpha used in the ELU function. So let's look at the recommendation for scale and alpha. These are some very peculiar, very long numbers that the authors recommend. And the idea here is to have something that the authors call a self-normalizing neural networks. And the authors argue that using this particular activation function with these very specific parameters leads to a network that has good properties and that actually does not need some of the complicated normalization layers such as batch normalization. So let's briefly look at this paper, self-normalizing neural networks. Then what you can see is that the authors put in a fair amount of work to argue exactly for why this is a good idea. And so you can see that this is a pretty long and extensive discussion of something that is ultimately very, very simple. Lots of pages of equations just to justify these design choices. So this is to demonstrate that since it's everybody's dream to write a paper about adding a single constant to an equation, that of course to get the paper accepted, you need to have much more compensation in terms of arguing really why this is a good idea and presenting lots of equations. Now, of course, this is a bit tricky because then in practice, while the idea might seem good, it's still not clear if this is beneficial, and this is also an activation function that's not commonly used. Here's another idea, and here you see the introduction of this division compared to RRelu. So you have e to the power of x divided by alpha as the change to the RRelu function. The shape again is very similar, and then there's another paper that argues why this is a good idea. So we'll just leave it at that. Let's look at another one. Hardshrink. We'll do some of these a bit quicker. So it's x if x greater lambda, x if x smaller than minus lambda, and 0 otherwise. So it's a linear function. Just around 0, it's clamped to 0. All right, that's how the function looks like. Looks a bit weird. Hardtanh, 1 if x greater 1, minus 1 if x smaller than minus 1, and x otherwise. So it's linear around the origin and clamped to 1 or minus 1 otherwise. All right, very simple, straight. Then here it's linear, and then here again, constant value. Log sigmoid, the idea is that sometimes the output of a sigmoid is processed by a logarithm, and it's more efficient to implement the sigmoid and logarithm together. So therefore there's a separate function that allows you to do that. So we have log of the sigmoid, and the sigmoid is 1 divided by 1 plus e to the power of minus x. This is the figure of the log sigmoid function. Softplus is an approximation to the RRelu function. The output is always positive, and you have this shape parameter beta that lets you select a trade-off between how smooth do you want it and how closely do you want to approximate the RRelu function. The default parameter for beta is 1. In addition, for really large values, that means large input values, over a threshold, the function reverts to a linear function for numerical stability. So if you have a very large input, let's say 1,000 or 10,000, then maybe you get some numerical issues. And then as an implementation detail here, the function just reverts to a linear function. Okay, output always positive. And you could try to plot this function and change the parameter beta and see how closely you can match the RRelu function. So here's some code I wrote to plot the activation function. And so here you can see the equation of Softplus, 1 divided by beta times logarithm of 1 plus e to the power of beta times the input. So time x here is the input. And okay, this is brute force implementation using a for loop, but okay, it just works. So what you see is that for the default parameter 1, this is a fairly smooth output, and now we'll set this default parameter to, we'll set this parameter to 10 and run it again. And then you see this looks already a lot more like RRelu, and maybe let's go 100. it starts to become very difficult to see with the naked eye that this is not the ReLU function. So I'm mainly showing this since I want to encourage a lot of programming and a lot of programming to try out small ideas such as plotting activation functions, plotting the derivatives of activation functions, just to get a better idea of what things do. And this helps learning also. If once you implement it, you might remember a bit better what the equations are and how things work. Softshrink, let's just look at the plot. So again, just goes up, then 0, and then linear again. Let's skip it. Soft sign. So soft sign is x divided by 1 plus the absolute value of x. We'll also not comment on this. We just show that it exists. 10h shrink. So this is x minus 10hx that has this particular shape. Threshold, output is x if x is greater than threshold, and otherwise it's a constant value. Softmin is interesting. It's the analog to softmax, and what you notice here, the difference to softmax is that we have a minus the value xi and here minus xj. So instead of taking e to the power of the input value and dividing by the sum of e to the power of all the other values, we do the same with the negative of the values. So softmin is a smooth approximation to the minimum, in the same way as softmax is an approximation to the maximum. Now, this one is the softmax function that we discussed before, and here you see the difference is that the minus sign here is missing and the minus sign here is missing. So let's flip back again just to make that clear. So minus sign here, and here it's the positive it's taking the values directly without the minus sign. The output values of softmax are in the range of 0, 1, and you can also look at the 2D version of the softmax 2D. Since the output of the softmax function is often processed with a logarithm, it makes sense to combine the two into one function, log softmax. And again, we saw that with sigmoid, combining these two functions together enables an implementation that is both more efficient and more stable. You can look on the net to get more details of why that is the case and what the difference in the implementation is if you're interested. The RRelu function is x times the cumulative distribution function of the Gaussian. So what you see, or the normal distribution. So what you see here is that now for the first time the function is not monotone. It starts out being close to 0, then it makes a dip below 0, and then it goes up again in an almost linear fashion. While this is something that is counterintuitive, we see this behavior in several modern activation functions. That means several activation functions that people tried recently and reported some success with. Another such function is the Swish function, which is x times sigmoid of x. One idea that is in neural architecture design is the idea of gating. You can use a function that is multiplied with another function, and a gating function maybe sometimes has the values between 0 and 1, and so what this gating function does is it either kills the signal, that means if it's 0, or it lets the signal through if it's 1. And what you see here is some sort of similar construction, and this is what the authors call self-gating. So there's this paper called Swish, a self-gated activation function, and here also the idea is it's a non-monotonic function, which is surprising, and the authors claim that this property is desirable and brings some advantage. And yeah, they promote this idea of self-gating. Now this function seems similar in shape. Again, it's like kind of linear here, then it dips down and goes out. And this function is defined by x. So you have this self-gating idea, x times 10h of soft plus x. So this is the smooth approximation to the ReLU. So x times 10h ln of 1 plus e to the power of x. Now, you can see that these functions look all very similar. So how can they be distinguished from each other, and what are the ideas to go into this function design? So in order to answer that question, you would have to go and read some of these papers. What I just wanted to say here, why I think this MISH function is very interesting is because it has been endorsed by Fast AI as making a significant difference in their tests, mainly on classification, neural networks, and you can read this blog post about it. But the people at Fast AI are extremely good at working on these practical competitions, and so when they endorse something, it's often a good idea to try it. Just one thing to point out about activation functions, as we now want to do some more of the summary of what we have learned, is that not all activation functions are differentiable at all points. So you can look at concepts such as the subgradient and the idea of left and right derivatives, and just let's take one example. So for example, ReLU does not have a defined gradient at 0. The left derivative is 0, the right derivative is 1. So you can just return one of these values in a software implementation if you use the idea of left or right derivatives. Also here, a short review of the subgradient. If we look at this function here, for example, this is the function f of x, and here the function is differentiable, so usually you get one derivative, one gradient, that can be visualized, at least in this simple 1D setting, as this line that is tangent to the function. However, if the function has a kink, such as at this point here, it's not totally smooth, so what you actually end up with, graphically speaking, you can fit multiple lines here such that the function is always above these lines, and so just you can look at the exact definition, but just visually, intuitively speaking, there seem to be a set of possible gradients that all fulfill the functionality of the gradient. So here the subgradient is a generalization of the gradient. So if there's only one possible gradient, then this is also the subgradient. And if you are at a point here that has a kink, there will be multiple possible subgradients. All right. So what should you use? I think ReLU seems to be a robust first choice. And then you probably want to read several papers specifically in your area and use whatever the best other networks in your field are doing. Now, another comment is that it is rare to mix different types of activation functions in a network, not in a motivated way. So often maybe the last layer is a classification layer, so there you might use a different nonlinear activation function than in other layers. But if you have, let's say, 10 similar convolutional layers, you would not randomly switch out activation functions. Still, activation functions are tricky. So since there doesn't seem to be a conclusive winner overall, some people go into the direction and say, okay, don't worry about it, just use ReLU and move on. So this is one good type of practical advice. However, there will be a difference somehow. So experimenting with different activation functions is just one part of hyperparameter tuning, architecture tuning that you might have to do if you really want to get the last final percentage of performance out of your network. And if you then look at some of the state-of-the-art architectures, you do see occasionally that people, or you do see it probably not unfrequently, that people say, no, we use something like Swish here, or we use Leaky ReLU here. And you do see a broad range of activation functions being used and recommended. You might also say that, well, why don't we just go and create a large test set and compare the performance of different activation functions to settle this debate. And there exist these papers, these review papers, these blog posts comparing activation functions. However, this is not so easy. So the activation function interacts with all other network components: the optimizer, the learning rate, the network depth, the type of network that you're working on, kind of the type of problem, the data that you use, the initialization that you use. And in general, it is too complicated to test all these parameters to come to a conclusive result. So you see some tests that can already see really large, that consider a lot of different data sets, a lot of different architectures, but this is often not enough, or this is typically not enough. That doesn't mean that if you somehow slightly change the architecture, have a different data set, that this trend, or that, you know, even if there's a perceivable trend in one of these tests, that this will apply to your work. So I would say there's a lot of caution that should be used when reading some of these comparative, these papers comparing different activation functions. Nevertheless, let's look at one such example that is done by a very serious and excellent group of researchers that typically have a vast amount of resources available. They come from Google, and so it is interesting what they read, since their work is backed up by a very large amount of experiments. So there's a paper that's called Smooth Adversarial Training, and here the authors claim that the smooth activation functions, they really noticeably improve adversarial training. Now, we'll look at briefly what that is. Let's just look at the result. So in adversarial training, there are two things we look at. One is what is the accuracy at the end, accuracy of the classification, but also what is the robustness to adversarial examples. And what you can see here is that while the classification accuracy doesn't change a lot, the adversarial robustness improves a lot by using other activation functions than ReLU. And you notice that several of these activation functions are kind of these smooth activation functions, and even the ones that are non-monotone and have this slight dip at the around the 0 range. So what are these adversarial examples that deep learning systems are concerned about and that adversarial training is concerned about? So an adversarial example is a sample that has been specifically designed by an attacker to cause the neural network to make a mistake. And one example is visualized below. That is a small noise function added to an image to cause a classification neural network to make a mistake. What you see on the left is an image of a stop sign that a neural network correctly classifies as a stop sign. And here an attacker finds that this particular type of noise added to the stop sign will cause the neural network to make a mistake. And the astonishing and also undesirable thing about these adversarial examples is that this noise function is multiplied with a very small scalar value so that it is unnoticeable for a human when it is added to an image, and the human can trivially, if looking at this image in blue here, can trivially decide that this is a stop sign, but the neural network now makes a mistake and it says that this is a sign of maximum speed 100. So this is a big drawback of neural networks, that they are susceptible to these adversarial examples. One thing, if you just add some random noise, then this would not happen. If you add noise that is specifically designed by an attacker, then you can get this effect. So there's a lot of discussion, a lot of theory, a lot of information about these adversarial examples, and hopefully we can spend some time later in the class to discuss more about them. But for now, let's just say that there are these small perturbations that can be optimized for by an attacker that will cause the network to make a mistake. So let's look at what is adversarial training. I basically only want to look at this equation here, and the traditional equation looks at the loss function of, with respect to the network parameters theta, the input image x, and the ground truth label y. And what we want to check is how well does the network using the input image x predict the ground truth label y. However, in adversarial training, there is this idea that there is an attacker that is allowed to modify the input image x by a small amount epsilon, so this epsilon has to be small and bounded somehow, that tries to cause the classifier to make a mistake. So in some sense what we're doing is we're not feeding the network with images and ground truth during training, but we let the network look at images that have been modified by an adversarial attacker that tries to cause the network to make a mistake. And this type of learning can help to make the network more robust to adversarial examples. So the graph here, this adversarial robustness, is some way to quantify how well a network is robust to these adversarial examples. All right, with that, I would like to conclude the lecture on activation functions.